Hello everyone, welcome to today's session. In this video, we'll start by understanding the concept of platform engineering, what it is, why it matters, and how it helps streamline modern application delivery. Then we'll move on to the hands-on part, where we'll deploy platform engineering architectures on both AWS using Amazon EKS and Azure using AKS. By the end of this video, you'll have a complete picture of how platform engineering works in theory and in practice across both cloud platforms. But before you move on with this session, make sure that you have subscribed to IP Specialist on YouTube and don't forget to hit the bell icon for updates. Now let's begin by understanding what platform engineering actually means. Platform engineering is the discipline of designing, building, and maintaining internal platforms that help software teams deploy, monitor, and manage their applications more efficiently. In simple terms, it's about creating a centralized self-service platform that provides developers with all the tools, automation, and infrastructure that they need, without requiring them to handle the underlying complexities. You can think of platform engineering as building a developer platform inside the organization, one that standardizes how applications are deployed and operated, so teams can focus on writing code instead of worrying about the infrastructure setup, configurations, or deployments. So now that we understand what platform engineering is, let's see how it fits into the broader DevOps and cloud ecosystem. DevOps focuses on collaboration between development and operations team to speed up software delivery, and platform engineering strengthens that goal by providing the actual tools and infrastructure that make DevOps processes seamless. Think of it this way: DevOps defines the culture and processes for faster delivery, while platform engineering builds that platform that makes those processes work efficiently and at scale. When combined with cloud technologies, platform engineering takes things even further. The cloud provides the flexibility, scalability, and automation capabilities needed to build these internal platforms, using services like Kubernetes, infrastructure as code, and CICD pipelines. In short, platform engineering brings DevOps to life in the cloud, turning best practices into practical, reusable systems that empower developers and accelerate innovation. Now, before we move ahead, it's important to understand the role of Kubernetes plays in platform engineering. Kubernetes is the backbone of modern platforms. It automates how applications are deployed, scaled, and managed across clusters of servers. Instead of running apps on individual virtual machines, Kubernetes abstracts the infrastructure and lets developers define what the application needs. The platform takes care of where and how it runs. In platform engineering, Kubernetes serves as the engine that powers self-service environments. It gives developers a consistent way to run applications across development, staging, and production, whether on AWS, Azure, or any other cloud provider. So, when we talk about building internal developer platforms, Kubernetes is often at the center, providing the flexibility, scalability, and automation that makes these platforms truly cloud native. Now that we know what platform engineering is, let's talk about why it's so important. In modern organizations, teams are constantly building, deploying, and scaling applications. Without a structured platform in place, every team ends up managing infrastructure in their own way, which leads to inconsistencies, wasted time, and a lot of manual effort. That's where platform engineering comes in. It helps automate infrastructure provisioning and management, ensuring the environments are created quickly and reliably every time. It also helps standardize environments across teams so developers can work in a consistent setup, whether they're in development, testing, or production. And most importantly, it increases developer productivity by removing repetitive operational tasks, allowing teams to focus on delivering features rather than managing infrastructure. In short, platform engineering helps organizations move faster, stay consistent, and operate more efficiently. Now that we understand why platform engineering matters, let's look at its core components, the building blocks that make it all work. First, the infrastructure as code, or IAC. This is where we automate the entire environment setup using tools like Terraform or ARM templates. Instead of manually creating servers or networks, everything is defined in code, making deployments faster, repeatable, and version controlled. Next, Kubernetes and containers. These form the foundation for running modern applications. Containers make applications portable and consistent, while Kubernetes helps deploy, scale, and manage them efficiently across environments. Then, CI/CD pipelines. Continuous integration and continuous delivery pipelines automate testing and deployment, ensuring that new features move from development to production quickly and safely. Next, monitoring and observability. Once applications are running, tools like CloudWatch, Azure Monitor, or Prometheus help track performance, detect issues, and maintain reliability. Finally, security and governance. Every platform needs to stay secure and compliant. Services like AWS IAM or Azure RBAC help control access, manage secrets, and enforce policies across environments. In short, these components together create a reliable, scalable, and secure platform that empowers developers to innovate without worrying about the underlying infrastructure. Now that we've explored the core components of platform engineering, let's see how these concepts come to life across different cloud providers. Every major cloud platforms offer its own set of tools and services to help organizations implement platform engineering practices, from infrastructure automation to container orchestration and CI/CD pipelines. On AWS, the focus is on services like EKS, the Elastic Kubernetes Service, for container orchestration, ECS for running containers at scale, CloudFormation for infrastructure as code, and Code Pipeline for building CI/CD automation. On Azure, we have AKS, the Azure Kubernetes Service for managing containers, Azure DevOps for source control and CI/CD pipelines, Azure Monitor for observability, and Bicep templates for infrastructure as code. Similarly, Google Cloud Platform offers GKE, Google Kubernetes Engine, Cloud Build for CI/CD automation, and Deployment Manager for infrastructure as code. IBM Cloud provides Kubernetes service and schematics for IAC, while Oracle Cloud supports Container Engine for Kubernetes and Resource Manager for infrastructure automation. In short, platform engineering applies across all major cloud service providers, each offering unique tools to build scalable, secure, and developer friendly platforms. In this session, however, we'll focus specifically on AWS and Azure to demonstrate how platform engineering is implemented in both environments. Now that we have covered the theory behind platform engineering, we'll move to the hands-on section. First, we'll deploy the architecture in AWS using EKS, and then we'll repeat a similar workflow on Azure using AKS. I'll walk you through the architecture, the prerequisites, and every command I run so you can follow along. This is the AWS architecture we will deploy for our platform engineering demo. At a high level, we have a VPC spanning two availability zones. Each AZ contains private subnets for Kubernetes worker nodes and public subnets for the load balancer. The internet gateway sits in the public subnet, so external traffic can reach the load balancer, and a net gateway sits in the public subnet to allow the worker nodes in the private subnets to pull images and updates. Worker nodes are managed by an auto-scaling group, and EKS provides the control plane and Kubernetes API. In short, this is a highly available production-style Kubernetes platform on AWS. Now, let's look at the requirements for this AWS demo. We need an AWS account with permissions to create EKS clusters, a browser where you can open the AWS console and access to AWS Cloud Shell. You should also be comfortable with basic kube control commands. I'll be using Cloud Shell for all commands so you can follow without installing anything locally. Alright, let's head over to the AWS Cloud Shell to begin the practical part of this demonstration. Alright, so this is the AWS Cloud Shell. First, let's make sure the required CLIs are available. In Cloud Shell, we're going to check for kube control, EKS control, and AWS. For that, we're going to enter some commands. First, to check the AWS version, we're going to enter this. Next, To check for kube control, we're going to enter the following command. And then next we're going to enter a command to check for EKS control. Now if any tool is missing, we'll install it. And as you can see over here that kube control and EKS control both are missing, we're going to install these. Now in order to install kube control, we're going to enter the following command. Next we're going to install EKS control. Now after installing, we're going to rerun kube control version and EKS control version to confirm that they're ready. So as you can see over here, we have successfully installed kube control and EKS control. All the commands that I'm running in the AWS Cloud Shell, I'll be sharing them in the video description for you to follow along. Now we're going to create the EKS cluster. I'll create a cluster named K8S example in the region EU West 2, which is the London region. EKS control automates networking, subnets, node groups, and more. So I'm going to enter the following command for that. This will take a few minutes. EKS control will create the EKS control plane, a VPC spanning multiple AZs, public and private subnets, and a managed node group backed by an auto-scaling group. Alright, so over here you can see that our cluster K8S example is ready in EU West 2 region. We can head back to Amazon Elastic Kubernetes service and see that it's active and up and running. Alright. Now let's confirm kube control can talk to the new cluster and check nodes and namespaces. For that we're going to enter the following command. Kube control get nodes. Now over here you can see that this command lists all the nodes in your cluster. Now we're going to view the pods and namespaces. For that we're going to enter the following command. So over here you can see all the namespaces currently running. Next, we're going to define a simple app manifest that deploys 5 replicas of a node app and exposes it with a load balancer service. I'll create the YAML file now. For that, I'm going to enter the following command and press enter. Next, I'm going to paste a script over here for it. I'm going to provide it in the description box. Now to save the file, we're going to press Ctrl O and press enter. Then to exit the nano editor, we're going to press Ctrl X. Now we will apply the manifest to the cluster. For that, we're going to enter the following command. Now over here you can see Kubernetes spin up 5 pods based on the deployment. If a pod fails, Kubernetes will attempt to recreate it automatically. Now let's get the service details to find the external load balancer endpoint. For that, I'm going to enter the following command. Now here you can see the external IP column is showing the load balancer DNS or IP. Copy the IP address and paste it into the browser. Your app should be live now. So let's copy it and open a new browser and paste it. So as you can see, that application is live and responding perfectly. Now I'll quickly show you a key feature in platform engineering, that is handling load. I'll demonstrate how quickly and easily we can scale our application using Kubernetes. For that, we're going to enter the following command and scale it up to 3 pods and press enter. Now to list these pods, we can use the following command. So you see how easily we have scaled the replicas to 3. Now I'll show you how we can scale back up to 5 replicas. So this shows how easily we can scale our application up or down using Kubernetes. Now after we have finished, we can delete the cluster to avoid charges. For that, we can enter the following command and this will delete the whole cluster. Now that the AWS EKS demo is complete, let's switch to Azure and build the same platform using Azure Kubernetes Service or AKS. We'll go through the architecture discuss what we need for this lab, and then deploy our application. You will see that while the environment changes, the overall Kubernetes workflow remains the same. So this is the Azure architecture we'll deploy for our platform engineering demo. At a high level, we have an Azure virtual network that spans multiple subnets. One subnet hosts the AKS clusters node pool. These are the virtual machines that run our containers. The cluster is managed by Azure's control plane, which is fully managed by Microsoft and integrated with Azure AD for authentication. We also have a load balancer at the front, which exposes our services to the internet, and Azure Monitor is enabled for observability and logging. In short, this architecture mirrors what we did in AWS, providing a production ready, scalable Kubernetes platform, but this time using Azure native services. Now, before we begin, let's quickly look at what we need for this Azure lab. An Azure subscription with permissions to create resource groups and AKS clusters, a browser with access to the Azure portal, and we'll use Azure Cloud Shell, so you don't need to install any CLI tools locally. All the commands will be run inside Azure Cloud Shell, and I'll share them in the video description for you to follow along. Alright, so this is the Azure Cloud Shell. We'll start by creating a resource group. In Azure, a resource group acts as a logical container to hold all the related resources, like your AKS cluster, networking, and monitoring components. So we're going to enter the following command to create a resource group and press enter. So this command has basically created a new resource group named My Resource Group in the East US region. You can replace the name and region with your own preferences. Next, we're going to create an AKS cluster by entering the following command. Alright, so we have successfully created an AKS cluster. This command actually does quite a lot. It creates the Kubernetes control plane managed by Azure, provisions one node in the cluster for workloads, enables the monitoring add-on which integrates with Azure Monitor, and generate SSH keys automatically for secure access to the nodes. This process usually takes a few minutes to complete. Now, once the cluster is ready, we need to connect kube control to it just like we did on AWS. For that, we're going to enter the following command. Now this command over here configures your kubeconfig file so kube control can communicate with the AKS cluster, and the second command, that is kubecontrol get nodes. This lists the cluster nodes, confirming that the AKS cluster is active and ready. Now let's deploy an application to this cluster. We'll use a simple microservices based app provided by Microsoft. It includes multiple components: a storefront service, order service, product service, RabbitMQ, and MongoDB. We're going to enter the following command and press enter. So this single manifest file creates all the deployments and services required for the simple application, showcasing how multiple microservices can run together on Kubernetes. Now let's take this one step further. A key concept in platform engineering is multi-tenancy. To demonstrate that, we'll create a separate Kubernetes namespace called Team A and deploy the same application there. This simulates different teams or environments sharing the same cluster while remaining isolated. For that, we're going to enter the following command and press enter. So this approach allows multiple teams to deploy their workloads in isolated namespaces, a common practice in enterprise-grade Kubernetes environment. Next, let's verify that our application is running and obtain the external IP of the load balancer so we can access the app in the browser. For that, we're going to enter a command. So this command watches the storefront service until an external IP address is assigned by the Azure load balancer. Once you see the external IP populated, you can just copy it and paste it in the browser to access the live stored application. So we're going to copy it and paste it in the browser. So here you go. So this setup illustrates how easily we can deploy a production style multi-service application in AKS, similar to what we build on AWS using EKS. Now after completing our demo, it's best to delete your resources to avoid any unnecessary charges. For that, we're going to go back to our Cloud Shell. So we're going to enter the command. Now this command removes the resource group and all its associated resources, including the AKS cluster, load balancer, and monitoring components. And that brings us to the end of today's session on platform engineering across AWS and Azure. We started by understanding what platform engineering is, how it helps teams automate infrastructure, standardize environments, and boost developer productivity. Then we explored its core components like infrastructure as code, Kubernetes, CICD, monitoring, and security. And finally, we put theory into action with our hands-on demos, first on AWS using EKS and then on Azure using AKS, seeing how both cloud providers enable us to build scalable, secure, and developer-friendly platforms. Platform engineering is all about empowering developers with self-service tools and reliable infrastructure, helping organizations innovate faster while maintaining control and consistency. If you would like to deepen your understanding of cloud and DevOps concepts, check out IP Specialist Comprehensive Certification courses. You'll find step-by-step learning paths, hands-on labs, and real-world projects to boost your career. Explore our cloud courses and DevOps courses. Start learning today and take your cloud journey to the next level. That concludes our session for today. Thank you for watching this video. If you found this video helpful, don't forget to give it a thumbs up and subscribe to our channel. And also share it with your colleagues or friends who might benefit from this information. If you have any questions or topics that you would like us to cover in the future videos, feel free to leave a comment below. Your feedback is very valuable to us.